All right, in today's assignment, we discussed how to evaluate determinants and apply the Cramer's rule. So, we're going to find different ways that we're going to use the determinant. First, we're going to talk about the area of the triangle, and then second, we'll talk about applying Cramer's rule. Okay, the determinant is a real number. You can remember that it is a number. It's only one number that you're trying to get, and it's associated with any matrix. And then it's found by taking the difference of the product of the diagonals. One way we can write it is DET A, and that says you're finding the determinant of matrix A, or we write it like this. And that is not an absolute value, that's associated with the matrix. So in example 1, we're going to be asked to find the determinant. So to find the determinant, we're going to look at the diagonals. This is called the primary diagonal, and so we're going to take the product of those diagonals. So here we would take 3 times 4, and then we're going to take our other diagonal, negative 1 times 5, and that order doesn't matter in multiplication. And then it says you're going to take the difference. So this gives us 12 minus negative 5, so we end up adding that. So our determinant is 17. On a 3 by 3, notice that both of these have been square. You will only be asked to do determinants on square matrices. On a 3 by 3, this is quite a bit different. A 2 by 2 has a lot less work. With the 3 by 3, the first thing that you're going to start doing is rewrite the first 2 columns. After you do that, then we're going to look at the diagonals, and we're going to have multiple diagonals here. We're going to look at all the diagonals, or the numbers in the diagonals that go this direction. All that go this direction we're going to add. So we take 5 times negative 3 times negative 6. Our second diagonal has the numbers negative 1 and 4 and 3, and the last diagonal in blue has the 3 numbers 0 and 2 and 7. And with a 3 by 3, we actually add these. We'll now look at the diagonals going the other direction. I'll draw them in green. And when you come back the other direction, you're going to actually subtract, and that's where you're going to get the difference of the diagonals. So the numbers in that first one that I drew, negative 1, 2, and negative 6, again, that order does not matter because it's all multiplication. And then we have a 5 in that next one, 4 and 7, and in the last one we have a 0. Anytime you have a 0 and you're going to multiply, it's just going to end up being 0. I could write those numbers 0, negative 3, and 3, but really all you need is that 0. And again, these last 3 you subtract. And then from here we just find out what those values are. In our first set of numbers we have 5 times negative 3 times negative 6 to give us 90. The second set we have 4 times 3 times negative 1, and the next one there's a 0, so it's a 0. Then we have minus, a negative 1 times 2 times negative 6 gives us positive 12. And in the next one we have negative 5 times 4 times 7, which is 140, and then at the end you have a minus 0. So you could actually just leave those zeros out, and from there you just add all of those up or subtract, and you should get negative 74. And remember that this is what the determinant is equal to. One reason that we use determinants is that it enables us to find the area of a triangle on a coordinate plane if you're given 3 points. Now, if you were asked to find the area of, say, this triangle here without matrices, then you would have to do quite a bit of work. You would first have to find the height, which would require you to use slopes because these two would be perpendicular. You'd have to find the distance between point A and B, and then you'd also have to find the distance between points C and D and use that information to find the area with the formula half your base times your height. Now if you have matrices, there's a really fast way to do this. This is our formula, area equals half of, and this is how you set up your matrix, but we need to know that these are actually determinants, so we show determinants by using those symbols. And notice we have our first ordered pair, second ordered pair, third ordered pair, and then to make it square we have a column of ones. And we will take half of that in the end, and that will give us our area. Okay, area should always be positive. If for some reason when you take the determinant here, if it comes out say a negative number, then you're just going to change that sign, and that could very easily happen depending on where the ordered pairs lie or the arrangement that you put them inside the matrix. So because we know that we're finding an area, we get to change the sign, and that's the only time you get to change that sign. So here's your 3 ordered pairs. You're asked to find the area, so we're going to take half, and then we're going to line these values up.
This is Sawyer Holly.
Our first one is 1, -1. Our second one is 4, 3. Our last one is 0, 5. And then again, we put 1s in our last column to make it a square matrix. Then to do this, remember that we have to rewrite those first 2 columns with a 3 by 3. And then we will use the diagonal method. There's another method that you can use to solve the determinant. It's called an expansion by minors. I can teach that to you if you'd like. You'll have to see me for during extra time to learn how to do that. So again, you're going to take your 3 diagonals, starting with that primary diagonal, and find the values. So we'll go ahead and just multiply those. So when you multiply the 1, the 3, and the 1, you get this 3 here. You multiply the -1 times 1 times 0, and you get 0. And you multiply the 1 times the 4 times the 5 to give you that 20. I somehow deleted everything, so if these have changed colors on you, sorry. We come back the other way with our other 3 diagonals, and we remember when we come back the other direction we subtract. So if I take the first diagonal here, those 3 numbers, multiply them, I get -1 times 4 times -1 becomes a -4. I take my middle diagonal, the 5 times the 1 times the 1, and I get -5, and the last one, there's a 0 in there, so 0 times 3 times 1 is just 0. When you have those 2 negatives together, they become a positive, and then we're going to just add those. And because we're looking for area, we have to take half of it. So we have 3 plus 20 plus 4 is 27, minus 5 is 22. We're going to take half of that to get 11, and then I like to say units squared, just in case we were to attach units onto that. And that is one way that we can use the determinant to solve the area of any kind of triangle. Okay, the last thing that you're going to learn in this lesson is called Cramer's rule, and we use this using determinants to solve systems of equations. If you're given a system of equation that looks like this, if you notice it's in standard form, ax plus by equals e, and cx plus dy equals f, then we're going to create a coefficient matrix, and it uses the coefficients in front of the a and the x. And if you can see, that's the a there, the b here, the c here, and the d here. And then we're going to use this matrix quite a bit. The first, it says here, Cramer's rule states, let A be the coefficient matrix if the determinant of A does not equal 0, and we'll revisit that concept in just a minute. Then the system has one solution at x equals, and it will equal the work that you do here. Notice you have the determinant of your coefficient matrix, and that would be this one here. And then you're going to create a new matrix for the top of that fraction. And you end up, if you notice, and this is how I teach kids to remember this, if you're solving for x, you replace the x column with the answer column. So EF goes there instead. Now, if you're solving for y, you replace the y column with the answers. So we're going to go ahead and try this. The first thing you want to do is set up your coefficient matrix. So A equals 2, 1, and these come from the coefficients in front of those variables, 3 and negative 2. And then from there you're going to find the determinant of A, and we do that by using diagonals. So you'll take those two, multiply them, you get negative 4, and subtract the other diagonal, minus 3, and we get negative 7 for our determinant of A. Then to find what x equals, we set up this matrix here, and we're going to divide it by the determinant of A, which is negative 7. So inside our matrix we will have, because we are solving for x, we're going to replace x with these two numbers. So we have 1, negative 23, and then this other column stays the same with 1 and negative 2. And then we'll solve this by multiplying your diagonals. So that gives you a negative 2 minus a negative 23, so plus 23 over negative 7, and I'm going to do it down here. So this gives you 21 over negative 7, which is negative 3. We do the same idea to find y. So y equals, because we're finding y, we leave the y column, or we change the y column, but we leave this other column alone. You notice that goes right there. And we're going to divide that by the determinant of A, which is negative 7. So again, you're going to do your diagonals. 2 times negative 23 is negative 46, and our other diagonal here, minus 3, and we're going to divide that by negative 7. So that should give us negative 49 over negative 7, and y equals 7. So this tells us that we have one solution because they are a system and they intersect at negative 3, 7. Now, I said earlier, I'll come back to you, if the determinant, in the rule it states if the determinant of A equals 0, then there is no solution. The solution does not exist. And the reason for that is if we were to put 0 here under our fraction, you cannot divide by 0. So that means it would be undefined in this case. And what that tells you is that these two equations are no solution. They do not intersect. Okay, that should help you be able to go through your assignment. I think 1 through 9, you can refer to example 1, A and B. 10 through 14 is example 2, and the back page is example 3. Good luck.